right. Welcome. I'm very, very pleased today to be able to introduce Professor Ali Sayed from the UCLA. I've known Ali for many years, from visiting UCLA when he was department chair and from my involvement in the IEEE Signal Processing Society. I think Ali has served in almost every capacity one could expect somebody to serve in the IEEE. He's done a huge amount of work, quite a lot in publications as the editor of signal processing publications, the vice president of publications, and serving at the IEEE tab level. So he's been very active. But the reason that I invited him and that lots of people are here today is because of his great technical work. So he's an author of more than 400 publications. He's won numerous awards, including the Technical Achievement Award in the Signal Processing Society this year and several other awards, many paper awards. Notably, some of the work he's talking about today was recently honored with a Signal Processing Society paperwork. I've also been looking forward to hearing this talk. I missed his talk recently at ICASP, his plenary talk, and so I figured I'd get him up here instead. He's noted as a great speaker. He's been an IEEE Distinguished Lecturer. He's won education awards, engineering education awards, the author of 5 books, so he's kind of done everything. And I have been especially selfish in inviting him here because he's working on a topic on learning and adaptation over networks that I think is one of the most exciting things that's happening right now in signal processing, and so I'm looking forward to hearing him. And with that, please welcome Ali.
Okay, thank you very much, Mary. That's very kind of you. She exaggerated a little bit, but that's okay. Okay, so thank you very much for coming to this talk. I appreciate it. I will be talking to you about the topic of learning and adaptation over networks. Okay, how do you move from adaptation over a single agent to adaptation over a network of agents working together? And how do you design networks of agents that function as a whole as an adaptive entity that's able to learn, adjust to changes in the environment, and solve meaningful problems? Okay, so if you are interested in this topic, I can give you references. Feel free to write to me if you are interested. Here I will focus on the ideas, the intuition behind the ideas, and try to explain what the results mean. So we don't have time to go through technical details or technical proofs. Okay, so this is more to motivate you about the main issues in this area. But before I start, let me tell you first, what is it that I will be talking about? So what is distributed signal processing? Because this talk falls into that general topic. Of course, you can define distributed signal processing in many different ways. One particular way is this one, which is good enough for the purposes of this talk. Distributed processing deals with the problem of extracting some global piece of information that's available in a dispersed manner across agents that are dispersed in space and that can collaborate with each other only locally. So let me show you an example. This animation is showing you an example. I have a collection of agents, and these agents would like to get to a target. At the same time, they would like to avoid some dangerous area. So each one of these agents has noisy measurements about the distance to the target and about the direction to the target. Each one of them has some of that information. So in principle, each one of them can just use its noisy knowledge and get there and avoid the dangerous area. But what if they can work together so that they can improve their estimate of where the target is and improve their estimate of where danger is and collaborate in this manner so that they can solve the problem more efficiently and more rapidly? So that's one example of distributed cooperation, where these agents share whatever little information they have with their neighbors and proceed in that manner so that they can solve this problem. So you can see from this example that a distributed solution has at least 3 elements to it. First, the agents have a global objective so that they can work together and benefit from sharing information with each other because they have a common goal. Second, the agents are dispersed. So they have access to information that's correlated, but is not necessarily the same kind of information. So cooperation can be helpful. And they can only talk locally to each other. So they are not collecting information from everybody in that area because they can be far apart from each other. That's not what this simulation is saying, but you can abstract to that case. Okay, so these are the elements or some of the elements that characterize a distributed solution. Now, there are many reasons why we would be interested in a distributed solution. I list some of them here. For example, there is always the power of cooperation. If you want to mine data that's dispersed, there is nothing more than putting many agents working together, accessing that data, and trying to extract as much information as you can from the data in a cooperative manner. Each one of these agents could be limited in its ability, but when you put them to work together, some power comes up out of this cooperation. The data may be available already in a dispersed manner, as happens with the cloud today. You have data all over the place. Or you may want, for example, to mine large amounts of data, as happens today in big data problems. In this case, you don't want to take that huge amount of data, send it somewhere to a powerful central processor to analyze it, extract whatever information you would like to extract, and then send it back to the individual agents. Transferring the data in that manner, and especially when you have large amounts of data, is very costly. Not only that, relying on a centralized solution of that manner can have a potential failure point, which is if the central processor fails, then a solution like this is not that robust, right? The solution itself will fail to operate. Whereas a decentralized solution where the agents are interacting with each other is if one particular agent fails, the solution can still continue to operate. There are also privacy and security issues. For example, agents may not be comfortable sending their data remotely. They may prefer to keep the data locally and process it locally with their own neighbors. So there are many issues that I mentioned here that justify or motivate the interest in distributed solutions. So motivated by these points, we are interested in designing networks that behave in this manner, where agents are interacting with each other. They can turn on their links, turn off their links. They can go to sleep. They can become active depending on the situation. They can trust their neighbor more. They can trust their neighbor less over time as they learn that you can be trusted more or less. So I would like to develop algorithms that allow a network of agents to behave in this intelligent manner such that the network itself becomes an adaptive entity. So I would like the individual agents to be adaptive, meaning that they can learn and they can adapt to changes in the environment. I would like them to have the ability to cooperate locally with each other. I would like them to be able to even adapt the topology and decide who should talk to whom and how much weight I should give to information I receive from you, and be able to even adapt that weight, because over time I can trust you more, I can trust you less. And on top of all of that, I would like this network to be solving something meaningful, solve a meaningful optimization problem. Okay? So this is the motivation behind what I'm going to be talking about. Okay? Interesting enough, okay, when you try to process information over networks, there are many degrees of freedom that come up that we don't have in this single agent case. And these degrees of freedom introduce challenges, and also they introduce opportunities. Many interesting patterns of behavior will come up that are not direct extension of the intuition we have from the single agent case, because agents are coupled now and influence each other's behavior. So for example, some of the degrees of freedom that you have now that you can control, in some cases you can control, like for example, the topology, who talks to whom, right? If you can control the topology, you can also control what kind of performance you can get. You can control how much weight every agent is going to give to information arriving over some link from some other neighbor, right? That also adds another degree of freedom. What kind of processing you are going to do locally, and how you are going to aggregate the information from your neighborhood, that adds another degree of freedom. So there are many degrees of freedom that now you have that you can control to try to improve the performance of a network like this. Okay? And not only that, many interesting questions come up, like I mentioned before, that are not direct extensions of results in the single agent case. But before I get into that, and before I explain to you what happens at the network level, let me spend a brief time, a few slides, reminding you of some classical results in the single agent case, okay, from stochastic approximation theory. And then I'm going to show you what are the issues that come up when you try to extend these results to the network case, okay? So the next few slides are not related directly to networks, but they are important aspects of the elements that I'm going to be talking about. So first of all, this is a generic problem. I'm interested in minimizing a cost function. Many problems, right, are optimization problems. I'm interested in minimizing a function j of omega. That's called a risk function, and omega is the parameter that I would like to estimate, the unknown vector I would like to estimate. Very often, especially in the context of adaptation and learning, the cost function is expressed as the expected value of some loss function. For example, in the mean squared error case, when the cost function happens to be the mean squared error case, the expected value of a quadratic error, the loss function is the quadratic error, okay? So I'm going to be using j and q, and just remember that j is the expected value of q over the distribution of the data. So how do you minimize problems like this? For this talk, I'm going to assume that the cost function is convex so that it has a unique minimum, and we don't have to worry about degenerate situations. That's good enough to convey the information. So how do people optimize cost functions like this? For example, you can use a steepest descent algorithm, right? Very widely well known and widely studied. You start from an estimate for your solution, call it W at time I minus 1. You update it by moving along the negative direction of the gradient vector of j. So you compute the gradient vector of your risk function, multiply it by a negative number, mu of I, and that mu of I can change with the iteration number. And that's called the steepest descent algorithm. So what's known about this algorithm? Okay. If the step size sequence is such that it diverges, but the energy is finite. For example, 1 over I. That sequence diverges, but 1 over I squared is finite. So if your step size sequence is of that form, c over I to the p for any p between 1/2 and 1, it is very well known that the steepest descent algorithm converges to the solution. Okay, this problem is very well studied. Okay. The problem is that in practice we don't know j, we only know q, and I'm going to give you an example very soon. So if you know q, how do you solve that problem? Okay. So people say, if I know q, let's replace the gradient of j by the gradient of q. Okay? So this becomes now a stochastic gradient algorithm, because now I'm introducing an error, which I'm defining as an S at the bottom of the slide. That's the difference between the gradient that you are using and the gradient that you would have loved to use, right? This is called gradient noise. So whenever you use an approximation like this, you are introducing some gradient noise into the operation of your algorithm. So what's known about this solution now? So under some reasonable conditions, technical conditions on the noise, on gradient noise, for example, it is 0 mean on average, okay? You can show that the algorithm still converges, which is interesting, okay? Of course, the convergence from towards WO will be bumpy, right? It will not be as smooth as in the previous case, because at every iteration you have some noise, but overall you are going to converge. That's a very good result, okay? So let's continue and show you an example to motivate that, okay? So this is a simple example. Let's assume that I have a channel with weights beta 0, beta 1 through beta 3, and I'm measuring the noisy output of the channel. U is the input signal, D is the output signal, and V is the noise with power sigma V squared, right? So you can write the input-output relation in that manner that I wrote up there, right? Okay? So this is a channel estimation problem. Given D and U, let's try to estimate the channel. Given the noisy measurement of the output and the input, let's try to estimate the channel. So how do we solve this problem? Okay, so let's collect the input data into a vector U. Let's collect the unknowns beta into a vector W so that I can write the sum more compactly as an inner product. This is just for convenience of notation, right? So the measurement is an inner product plus noise. I know U, I know D, I would like to estimate the channel W0, right? This is a channel estimation problem, very common in many, many different contexts. So one way to solve this problem is to formulate, for example, a mean square error estimation problem, the J over there. So find the omega that minimizes the mean square error between D and U. I'm given D and U. Find the omega that minimizes the mean square error. So you can see that J has the expectation, and Q, which is the loss, does not have the expectation, right? So that's the difference between J and Q. So if you write down the steepest descent algorithm and the stochastic gradient algorithm to minimize this problem, you are going to get the two recursions that you have here, okay? So you have the risk on the left, the loss on the right. If you expand the risk function, because of the expectation, you need to know the moments of your data. You need to know the statistical distribution of your data, which I'm calling RDU and RU, second order moments, so that you can evaluate J and you can evaluate the gradient of J, right? So you can see here that it depends on the moments of your data. So to run the steepest descent algorithm, you need to know the distribution of your data. When you don't have that, you can run the stochastic gradient algorithm, where you instead replace the gradient of J by the gradient of Q. When you compute the gradient of Q, it depends directly on the data, right? So this algorithm, you can apply it directly, right? You just have the D's and the U's, and you run this algorithm, okay? And like I said before, under certain conditions, this algorithm will converge, okay? Very good. So what's the point now, okay? So you would like to use the actual gradient, but you don't have the actual gradient. You end up using the approximate gradient. We call it an instantaneous approximation for the gradient. And the difference between these two, I called it the gradient noise, okay? So don't worry much about the algebra, but if you subtract these two, you will get an expression like the one I'm showing here. The interesting thing about this expression is, even though Wi is converging to Wo, so that the first term disappears over time, the second term will not disappear over time. The second term has noise and has regression vector U. That term is always present, even though your algorithm is converging. So we say that we have an absolute component in the gradient noise that never disappears. Okay, I'm going to come back to this point later. So I'm denoting the variance of that by that notation R sub S. Just remember, it depends on the noise variance and on the covariance of your data. So even though you are converging, there is a component of the gradient noise that's there. Okay, so why do I say this? You'll understand it very soon. Okay, so let me show you another example, okay, and then I'll comment on this point. This is another example. I showed you a channel estimation problem. This is a pattern classification problem. I have two sets of data. One set belongs to class 1, the other set belongs to class -1, and you would like to find the equation of the hyperplane, that blue line that you have there that separates the data. Okay? So there are many ways to solve this problem. I'm just showing here one way. For example, you can choose your risk function to be the expected value of a certain Q that I'm showing here, which is called the logistic function. Okay? So given the feature vectors xi, and given the labels where xi belong to, I can use this data to try to minimize this cost function, and if I do that, I end up with an equation for the hyperplane that separates the data, right? This performs the pattern classification for you. So if you do this, you end up with that algorithm, the stochastic gradient algorithm. Just compute the gradient of Q, you end up with that recursion. And you have the step size sequence over there. Now, when you are using a step size sequence like that that decays with time, what happens is mu of I times the gradient of Q will die out with time. So the algorithm will stop adapting, will stop updating when your step size gets close to 0. So then you can't solve situations like this where the hyperplane is changing over time because the nature of your data is changing over time. And the algorithm will not be able to track solutions like this. So that's why we are interested in solutions where the step size is a constant. Okay, the step size does not change with time. Because once I fix the step size to a constant, I now enable the algorithm not only to learn, but also to adapt, to adjust with changes in the nature of your data and continuously learn. Because if mu is a constant, you will never kill that second term. However, remember that The gradient noise has a term that's persistent. Even if the algorithm functions properly, that absolute component of the gradient noise is always there. And if mu is a constant not going down to 0, that term will always be there. Okay? So this will come at a price. You are going to adapt and you are going to learn, but your algorithm will do that at a price. Okay? So for the example I showed you before, where your loss function was quadratic, if you just repeat the same argument, you get the famous LMS algorithm, by the way, for those of you that are familiar with that. Okay? So at what price does this come up? Okay? So there it is. Let's define the error between what I want, WO, that's the minimum of the cost function J I'm trying to minimize, and WI is the estimate that the algorithm is giving you. There is an error. This error is not going to 0 now. In the constant step size case, it's not going to 0. It's going to some level. How small is that level? So we measure it by measuring the variance of the error in steady state. That's called mean square deviation. Okay? It's not going to 0, but it's going to become very small. Let's measure how small it is by measuring its variance, okay, the mean square error. So there are results in the literature, okay, and these are the results, for example. I defined RS before. This is the variance of that persistent noise that's always there. I called it R sub S. And let's define the Hessian matrix H. That's the second derivative of your cost function at the solution. It turns out that the performance of an adaptive solution will always depend on these two parameters in a manner that I write here. So don't worry about the expression, but let's explain what the expressions mean. How small the mean squared error is. The important fact is that it is of the order of the step size. So small step sizes will allow you to learn well. That MSD will be very, very small. But there is a compromise, a trade-off. A small step size, alpha is the convergence rate. It's an idea of how many steps you need to get to steady state. So very small mu can make the convergence rate alpha close to 1, and therefore the algorithm will converge slowly. So this is a trade-off between tracking well and learning well. Okay? But the important conclusion you get from here is that if I use constant step size, I can still learn, I can adapt, and that comes at a cost, but fortunately it's a cost that I can afford. It's of the order of the step size. And if the step size is small, then my algorithm is going to learn well. Fine, so this is the brief summary of stochastic gradient approximation theory. Let's now get closer to networks. Let's assume now that I have two nodes. Let's start with the case of two nodes. I have node 1, and node 1 receives data D1, U1, and wants to estimate the channel. So it can run its own LMS algorithm. And using the expression I just wrote on the previous slide, we know exactly how well this algorithm will perform. That expression in the quadratic case reduces to this. It's proportional to the step size like I showed you before, but also proportional to how much noise you have in the data related to node 1. Now let's assume node 2 solves a similar problem, receives its own data, D2 and U2, and runs its own adaptive algorithm. It will learn the channel. And how well will it perform? It will have a similar expression. But observe now that node 2 will perform as well as the level of noise that it has. So the node that has less noise power will perform better, will get better MSD. So if these nodes are solving the problem on their own, the noisier node will perform worse, right? This is natural. So now, can I put them to work together to do better? So let's assume first that these two nodes send the data to a central processor. So the central processor has the entire set of data. Of course, the central processor, being powerful, can implement whatever sophisticated algorithm, right, it might consider. But here, I would like to consider algorithms of the same family, stochastic gradient algorithms, to keep the comparison fair. So let's assume the centralized processor is running, again, a stochastic gradient algorithm. So it's going to use the data it receives from both nodes, 1 and 2, average the approximation for the gradient direction, and move along that direction. Right? That's how the centralized solution is going to perform. So what's the performance of the centralized solution? If you repeat the analysis, you will find that the performance is similar to what you had before, but the noise variance now is replaced by the average noise variance. Now, the average of two numbers lies in between, right? So you can see that the centralized processor will perform better than one of the nodes, but not necessarily better than the other node, right? If the centralized processor is using a stochastic gradient algorithm of this manner, that's what you can expect from its performance. So let's assume now I do something different. Let's assume now that I allow these nodes to remain distributed and share data with each other. Can I do better than that? Okay. One way to do it, for example, is by using a diffusion strategy, okay, to diffuse information, and this is how it works. Node 1 will still run the first equation, that's the LMS update, but it's going to call the result psi1, an intermediate value, not the next value of its W estimate. Node 2 is going to run the second equation, but it's going to call the result of psi2. That's an intermediate value. It's not going to call it the updated value for its W2. And then the nodes exchange their psi's, as you see in these equations. They exchange their psi's and combine them in a convex manner. Node 1 uses alpha and 1 minus alpha. Node 2 uses beta and 1 minus beta. And that becomes their updated estimates. So in comparison to the standalone LMS filters that they were running individually, now they are running LMS updates, but then they share the estimates, combine them, and the results are used back for the next iteration, and the process continues. Okay? So this is one example of a distributed strategy. Okay? So now I can ask questions like this. Can I choose the coefficients alpha and beta to ensure that the performance that these nodes are going to achieve when they share information like that will be better than the best among them before sharing information? And the answer to this question is yes. Can the performance match the centralized solution? And the answer is yes. Now, the interesting thing that you might ask here, how can I match or exceed the centralized solution? It's because in this distributed solution, you are using additional information that the centralized solution hasn't used. You are using these parameters alpha and beta that you can design. If you go back to the centralized solution and you modify it to add weights to the data it receives from the different agents, then you can make the centralized solution match this solution as well, okay? So the important thing, what this result will be showing, and later I will be showing you expressions, is that the distributed solution doesn't limit your performance. It can match the performance of the centralized solution if you design it well, okay? Now, if each one of the agents can estimate the solution on its own, if I put them to work together like this, can the network become unstable? The interesting answer is if you combine them in the wrong way, the network can become unstable, okay? So these are, for example, if you use the consensus strategy, which I'm going to describe later, okay? So I'm going to comment on the answers to these questions more broadly in the context of n-agent networks, not just two nodes, okay? So let's now go to the case where I have more than 2 nodes, multiple nodes, 1,000 nodes. So if I have multiple nodes, now you have the topology is the degree of freedom. I can connect them in many, many different ways. I can allow them to share information in many, many different ways, right? You can have hundreds of ways depending on the number of agents that you have. So now these become important questions. If I give you many different topologies to solve the same problem, which one should I choose? Which one will converge faster and will get closer to the solution, to the minimum of my cost function? Okay? For example, can I take any one of these solutions, networks, or topologies and make it match the solution of the centralized algorithm? Okay? So does the topology matters, or is it more important the choice of the alphas and betas, how they combine the information from the neighbors? Okay? These are important questions. I'm going to answer them. Okay? But to answer these questions, I first need to understand how the performance of a network trying to solve an aggregate optimization problem, as I'm going to show you, how the performance of that network depends on the topology of the network, what kind of convergence rate and mean square error I can expect as a function of the topology. The challenge here is that these agents interact with each other, so they influence each other's behavior. But we can still say something meaningful. So let me formulate the problem now, okay? And then show you the conclusion. So I'm now moving to a general network, okay? I have a network of n agents. Each agent has a cost function associated with it. For example, agent L has some cost function J sub L. It may be the case that all costs are exactly the same, that all agents are interested in minimizing the same cost function. That happens often, for example, in machine learning applications. But for generality, let's assume that these cost functions are not necessarily the same. Okay? The neighborhood of a node, for example, node K here has neighbors L, 7, 4, and K itself. These are the agents with which it can share information. Okay? So I'm interested in solving an aggregate optimization problem of that form, minimize the aggregate cost, which is the sum of the costs over the network, subject to some constraints, convex constraints, for example, inequality constraints or equality constraints. So where do these constraints come from? Because agents may have different levels of information about the unknown you're looking for. Some agents may know something that other agents may not know, and that reflects into the type of constraints that you have at the different agents. Okay? So here I will not be solving the constraint problem. You can approximate it well by using an unconstrained problem. So I'll focus on an unconstrained problem in this presentation. Okay? So assume I want to minimize an aggregate sum like that. I'm going to continue to assume that my cost functions are expectations of loss functions. Okay? So how do I solve a problem like this? Okay? So there are many algorithms to do that. Okay? A few years ago, we introduced this class of algorithms which we refer to as diffusion strategies. Since then, they have been studied by many other colleagues. I list some of them here, and this is how the diffusion strategies work. Look at the first equation. So now I have a collection of agents trying to learn, optimize something. Every agent, for example, agent K, is going to run the stochastic gradient update, the first line. This is exactly what I did before. You start from its estimate, W at node K at iteration I minus 1. You move along the negative direction of its loss function, and you call that an intermediate value psi. In the next step, agent K is going to aggregate the intermediate estimates from its local neighborhood, right, N sub K. And every other agent in the network is doing the same thing. So at every iteration, every node adapts. Okay, that's called learning. And then social learning is the second step where you learn from your neighbors. Okay? So that's called the diffusion strategy, and it's called adapt and combine form because you are adapting first and then combining. So let me mention a few remarks about this. First of all, the step size is constant because I want this network to continually learn, and I'm going to show you an application later. Second, observe that the estimates on the first equation that I'm starting from are exactly the same. Okay, this is important. This symmetry is important, okay? There is another form of the algorithm which I call CTA. You combine before you adapt, and sometimes it makes a difference. So you do the combination first, and then you adapt. Okay? Again, symmetry is there. The same estimate is used on the right-hand side of the adaptive equation. So this is called the CTA version. Now, this form of the algorithm is closer to another form of the algorithm called consensus algorithm. Okay? In system theory, in control theory, it's a popular algorithm, and it looks like this. It's similar to the second form of diffusion with one important difference. Okay? And the important difference is that the weight estimates that you are using on the right-hand side of the second equation are not the same. That introduces an asymmetry into the dynamics of the algorithm. You see that the first one is the intermediate value, but the second one is the value that you started from. When you are using constant step sizes, you can show, we have shown that in recent work, this leads to an unbounded growth in the state of the consensus network. Okay? So for adaptation and learning, I will be focusing on diffusion strategies for that reason. Because when the step size is changing with time, that's fine, perfectly fine. But when the step size is a constant, the gradient noise is accumulated in such a manner that the asymmetry leads to instability. So I will be focusing on diffusion for that reason. Fine. So I have the algorithms that I can use now to solve this distributed optimization problem. How do I evaluate its performance? Okay. To do that, now remember that I have a collection of agents. Each agent has its own estimate WK of the unknown that they are looking for. So each agent has an error W tilde K associated with it, right? So let's define the steady state value of that error, which I'm calling MSD at node K, mean squared deviation at node K. And the average over the nodes is the MSD, is the performance of the network. So I would like to know how well each node performs and how well the network performs. Are they able to learn the solution? Okay? So to get to that, to state the results, okay, let me first introduce some minimal notation, okay? I have n agents interacting with each other, and each agent is using a set of convex combination coefficients to combine the data from their neighbors. So I can take all these coefficients and collect them into a matrix A. This will be an n by n matrix. This matrix reflects the topology. If you look at the entries of this matrix, you can tell who is talking to who and by how much they are scaling the information they are receiving from that neighbor. Okay? Because these weights are convex combination weights, this matrix will have this useful property. The entries on every column of the matrix will add up to 1. Okay, this is called the left-stochastic matrix. And because we are dealing with networks that are connected, and I'm going to assume that at least one of the diagonal elements of this matrix is strictly positive, meaning AKK is positive for at least 1K, which means that at least one node in this network trusts its own data, okay, which is a reasonable assumption. When that holds, it means that this matrix has a certain property it's called a primitive matrix, okay? In that case, it follows from a famous theorem called the Perron-Frobenius theorem that the matrix has a single eigenvalue at 1. All other eigenvalues will be inside the unit circle. We already know a left eigenvector, which is the vector of all ones. Let's denote the right eigenvector by P. Let's normalize its entries to add up to 1. Then it follows from this theorem that all the entries of P will be between 0 and 1, and they add up to 1. So the entries of P have an interesting interpretation. You can interpret them as probability measures. They add up to 1, and they are positive. And the entries of the vector P are determined by the topology of the network, because A reflects the topology and the weights, and P depends on that. Okay? So this vector P will be critical in telling you how well these networks perform. Okay? These are just examples to show you we can compute P in certain cases. I'm going to skip that just to stay on time. So I have two results that I would like to share with you. The first result is this one. Okay? Remember that we started by saying I would like to converge to the minimum of that aggregate cost function. Now, from calculus, we know that the minimum of that function should be the solution of this equation, the sum of the gradients equal to 0. But that's not what the network will end up doing. You can show that the network is actually converging to the weighted sum of the gradient vectors equal to 0. Okay? And the weights are the step sizes and the entries of that vector P that I showed you. So this is an interesting conclusion. Okay? It tells you that there is some flexibility in this network. By designing A and therefore P, I can guide the network to converge to points that might be more interesting to me, rather than always converging to this solution. So through the control of A, you can control the convergence point of your network. Of course, in the special case when the step sizes are constant, where Pk is a constant, all the entries of P are the same. This happens, for example, when the combination matrix is doubly stochastic, meaning not only the columns add up to 1, but the rows also add up to 1. Okay? So in these cases, that mu k pk gets out of the sum, and you are converging to this. Okay? And doubly stochastic matrices are very common, for example, in consensus implementation. That's the case. Okay? So you don't see this issue. But in adaptation and learning, it turns out that we are interested in combination matrices that are not that are not specifically doubly stochastic. They can also be left stochastic, and you can show that best performance is achieved with left stochastic matrices. So then this issue comes up. Okay? So this solution has an interesting interpretation also as a Pareto optimal solution. Let me explain to you what that means. Assume you have two agents. Okay, Jk, J sub L, that's the cost of agent K. This is the cost of agent L. If agent K is solving the problem, it will converge to its yellow solution, yellow cross over there. If agent L is solving the problem on its own, it will converge to the yellow cross on this side. The aggregate cost is some cost function that looks like the red curve. Ideally, you would like to converge to the red circle. That's the minimum of the aggregate cost. But the algorithm is converging to the yellow circle somewhere else. Okay, somewhere else. So if these agents work together, they will end up converging to that yellow circle. So what's the interpretation of that yellow circle? Let's assume that the blue agent wants to move to the left to get closer to its minimum and reduce its cost. Then if the green circle moves to the left as well, its cost will go up, so that's not good for it. If the green agent tries to move to the right to get closer to its minimum, that will force the blue agent to move to the right and therefore away from its minimum. So a Pareto optimal solution is one such that if one agent tries to get better performance for itself, it will harm all other agents in the network. Okay? So for cooperative networks, that's not necessarily good. That kind of behavior is not good. So a Pareto optimal solution is well suited for cooperative networks, and the algorithms we have will help you converge to solutions of that kind. Okay? Let me share you another result just to stay on time. Okay? Fine. I know that I converge, and I know where I'm converging to, but how close do I get to it, and how fast do I get there? Okay? For that, let's remember the definition of the gradient noise. It's the difference between what you want to use and what you are using, the gradient of Q and the gradient of J. I defined the covariance of the persistent part of that, the part that doesn't die out, even if you converge. I called it R sub K, if you remember. And H sub K is the Hessian of the cost function that the agent is trying to minimize. It turns out that the performance of the network can be captured only in terms of these two parameters. Okay? So with every agent in my network, I can associate these two parameters, the Hessian matrix of its cost and the covariance of its gradient noise, the persistent component of that. I can also combine them in this manner, trace of H inverse R, and replace them by this scalar theta. I can capture the performance of the network in terms of these parameters. And this has an interpretation related to a signal-to-noise ratio measure. So what's the result? Don't worry about what the equations are, but let me explain to you what the equations are saying. Okay, this is the result. The first line of the equation is saying, if you want to solve that problem, minimize that cost function in a distributed manner, all the agents in the network are going to converge to similar mean square error performance. They are all going to get equally close to the solution. That's what the first line is saying. MSD is the MSD of the network. Meaning that even if some agents are noisier than the other, that effect is going to be equalized across the network, and all agents are going to perform equally well. That's number one. Number two is a very interesting expression. What you have a combination of the Hessian matrices and a combination of the noise covariances, and they are weighted by the mu times p. Remember that p reflects the topology. So what this expression is telling you, it's telling you how the performance of the network depends on the topology. So now if you give me two different topologies, I can tell you which one among them will give you better performance. Because for different topologies, I have different P's. I can come here and tell you which one is going to perform better. And the last line is telling me the rate of convergence of that topology. I have an expression for it that also depends on P. I can tell you which topology is going to converge faster. So now I have a way to tell you, if you give me different topologies for solving the same problem, which one is going to learn faster and which one is going to converge closer to the solution. You can do that because now you have expressions like this. These expressions actually tell you more than that, okay? So let's look a little bit further into that, okay? Assume now I ask the following question. I want to do now a design problem. Everything so far has been mostly analysis. I'm analyzing the performance. But now I want to do design. I ask the following question. If I'm allowed to pick the topology, which topology should I pick to always get the smallest, or to get the smallest mean square error in steady state? right? I can ask that question, right? Under some conditions, you can solve that problem. It turns out that the optimal solution is the left stochastic solution. It's not a doubly stochastic solution. And not only that, here I have an expression for the optimal A that you can use to get the best performance. We call it the Hastings rule. So there are two things that are interesting about this result. First, that the best solution is left stochastic, not doubly stochastic. Second, the optimal solution depends on those thetas, those signal-to-noise ratios. This is very much different from results or from constructions that are typical in graph theory. For example, over there you have choices for this A in terms, let's say, metropolis constructions or other constructions where the weights that the agents use depend on how many neighbors I have. For example, in the averaging rule, if I have 3 neighbors, I'm going to assign weights 1/3 to each one of them. Okay, that's one rule. Okay? In the metropolis rule, I'm going to see how many neighbors she has, how many neighbors I have, and I'm going to choose the maximum of that, and the inverse of that becomes the weight. But regardless of how you do it, the weights are always chosen in a manner that depends on how many neighbors you are, how well connected you are. From the point of view of adaptation and learning, that's not enough. I should also take into account how noisy you are. You know, I don't care if you have few connections or too many connections. If you are too noisy, that should also influence the result I get from sharing data with you. So you see that the optimal solution is information aware. It doesn't only depend on the size of the neighborhoods, but these are scaled by how much signal-to-noise ratio you have at these agents as well. So that's another important conclusion that's relevant in the context of adaptation and learning, which you don't see in other constructions, okay? So that's one conclusion. Another interesting conclusion that follows is this. I'm repeating the expressions here, okay? The mean square error performance on top and the convergence rate on bottom. So you can see that mu, p are positive, and h is a positive definite matrix. Now I can ask the following question. If I add more agents to my problem, if I increase n, does it help me? Does it give me better result? You see, if I add n, this sum becomes more positive. I'm subtracting it from 1, so alpha becomes smaller, so the algorithm will converge faster. However, the MSD expression, if I increase n, because of the inverse and the multiplication by the other sum, that combination can go up, can go down, can remain invariant. So adding more agents is not necessarily always helpful. It may improve convergence, but you may be converging to a worse MSD level, to a worse solution. Okay, that's a very interesting conclusion that comes up when you're trying to learn. So if I go from a situation where I have few agents to more agents, you may improve your convergence rate, but the MSD performance may get worse. Okay, so that's another conclusion you get. This is, again, like I said before, many results come up that you wouldn't expect from the theory of single agent adaptation and learning. And the last point I want to show you before I show you 2 examples is this. I mentioned earlier that the asymmetry in the update leads to instability, and this is a useful point to remark. I'm repeating here one form of diffusion on top. You can see that the weights used on the right-hand side are the same, and the consensus strategy at the bottom and the weights used on the right-hand side are asymmetric, different. That's the updated weight. This one is the previous weight. Because of that, the stability of consensus networks is very much topology dependent. It can be stable in some cases, it can be unstable in other cases, whereas diffusion is always stable. So let me show you why, what's the reason. Okay? So this is the theorem that we have, that consensus networks can become unstable, and diffusion networks will learn faster and give you better mean square error performance in steady state. Let me explain to you the reason behind that. Okay? If I collect the errors across all agents into a big vector, so I call it W tilde I, the evolution of that error follows that. The evolution of that error follows that equation that you have there with a coefficient matrix B. Okay? In the non-cooperative case where the agents are working on their own, that matrix B is a diagonal matrix. Let's assume that's stable, so that the agents are stable. In the diffusion case, that matrix becomes the combination matrix times the diagonal matrix. In the consensus case, it becomes the difference. And then a matrix theory result tells you that if I minus D is stable, no matter what combination matrix you use, the product A transpose times that will always be stable. So if the agents are individually stable, no matter how you connect them and you run diffusion on top of that, it will always be stable. That's not the same case for consensus. And this makes sense. Think about it. If I have a scalar I minus D that's less than 1 in magnitude, if I multiply it by a matrix A that's always less than 1 in magnitude, the result will always be less than 1 in magnitude. But that's not always true for the combination like the last line. So that's where the instability problem comes up from, okay? So let me now show you 2 examples, and then I'm going to conclude, okay? 2 examples to illustrate where you can apply these results. The first example is in the context of constrained optimization. Let's assume I want to solve a minimization problem like that, an aggregate cost, subject to some constraints. What that means is that the solution lies within a certain convex set. So if you apply the algorithms that we just derived, you can get solutions that behave like that. Even if the convex set, even if the constraints are changing with time, you can track where the solution is. Because this is an adaptive solution. You are using a constant step size. You end up with a network that's able to learn, and not only that, track where the solution is going. So that's one useful application. Another application, let's assume that I have a network of agents, and one of them is malicious, or one of them is defective, and it's feeding you wrong data. I haven't talked here about adapting the combination weights as well. You can do that as well. These combination weights, they do not need to be fixed. I can also adapt them, because with time I can learn whether you are a good neighbor or a bad neighbor. So if I allow a network to learn who is good and who is bad, I can end up disconnecting and assigning small weights to neighbors that are bad, right? So I can do intrusion detection, I can do clustering, for example. This is an animation, a video animation. So for example, in this algorithm, I have the combination step here, and right before it, I have the equation that allows me to adapt these weights by measuring how far what you are giving me is from what I expect. Using that type of analysis, you can come up with algorithms to adapt the combination weights as well, and you can get this type of behavior. You see here that's a counter that's running up there, and you have an intruder. This network is assigning weights to the links, and you are going to see as it converges, some links will be thicker than others, meaning I trust this neighbor more, and the links to the intruder will be cut, will have very small values because the network learns that this intruder is defective or malicious, right, and so forth, okay? So I'm going to conclude here. So I gave you an overview of results we have in the context of adaptation and learning and optimization over networks using algorithms that are able to adapt and track the solution if it changes over time, right? And I explained to you how do you evaluate the performance of solutions like that, what issues come up when you connect agents in that manner. Now you have the additional degree of freedom of the topology, so how do you design the topology? How do you compare different topologies, right? And there are many other interesting issues. For example, if some of the agents are selfish, they don't want to share information with you, how do you entice them to share information with you? I haven't talked about that. Okay, so I'm going to stop here, maybe take some questions just to stay on time. Okay, thank you.
Questions?
At one point you mentioned that the distributed algorithm achieves a Pareto optimal solution, but not necessarily the global social optimum. What determines the gap between those two? Is it the network topology or the weighting scheme you use?
Right, so his question is about the issue I mentioned before about the network converging to the Pareto optimal solution, right? So what I showed is, you see, the global solution that you are interested in is one of the Pareto optimal solutions in the example I showed you, okay? And that problem has many Pareto optimal solutions. Any solution between the 2 yellow crosses will be a Pareto optimal solution. Which one you converge to depends on how you choose the topology, because that influences the P's, and how you choose the step sizes, because the step sizes can change across the agents, okay? So these 2 elements, the topology and the step sizes, will determine which one of them you are going to converge to. Now, if you are interested in converging to a specific one, so that then you can do a design problem, which is let me pick the A and therefore the P in such a way I get to that one, okay?
Other questions?
You mentioned that step size, if the step size is always the same, that there are stability issues, I think, with single agents, if I got that right.
There are what? Stability issues?
Stability issues with single agents if the step size is constant.
Okay.
If there are step size issues with, aggregates.
Yes, of course. When the step size is a constant, even in the single agent case, it has to be small enough, smaller than a certain bound, so that stability is guaranteed. And people have results on that, and we know what these bounds are. Similar issues occur here. You can determine bounds on how large these step sizes can be without destroying stability, and we have these bounds, okay? Why is that? Because of that persistent noise that's there, you would like to ensure that the dynamics is stable. That leads to a bound on the step size, and we have these bounds. I haven't shown them here, but these bounds exist, okay? Yeah.
Other questions? I'll ask a quick question. In the examples that you have here, it looks like there's a fixed n, but some interesting networks have varying n, so agents might come or go. In particular, often they get bigger. How does that, roughly how might that affect some of the results?
Yes, good question. Okay, you see, there are two elements to this. Okay, first of all, observe that the performance expressions depend on the number of agents. So I know how the performance will change as the number of agents changes and as the topology changes. So this result that I talked about, adding more, making more agents informed or less informed, and how that influences the performance, that's one aspect of this. Agents come in or leave. There is another aspect to it. I focused here on cooperative networks where behavior is synchronous, meaning that the data is arriving at the agents synchronously at every instant of time. But you can also study asynchronous behavior, where data comes at different time. Agents may adapt. Some agents may adapt now. Other agents may adapt later. So the behavior is not synchronized. That captures the second aspect of your question. You can also study performance under these conditions, okay, where random events can happen in your network. Edges can turn on and off. Agents can turn on and off. They can adapt. They need not adapt. The interesting results that we have is that the mean square error performance of the algorithm is affected, but only by a small amount, while the convergence rate stays almost the same. Okay? What that means is that these networks are extremely robust to random events like that, as long as the network on average stays connected. Yeah, you can prove results of that nature. Yeah. Yes?
In some of these results, so what if the agents have dynamics? Can some of these results work for that case as well?
Right, very good question. One example, so he's asking what if the agents have dynamics? One example of a situation that we studied where the agents have dynamics is when the agents have state space models with a particular state vector, right? And they are observing noisy versions of that state vector, and you want the entire network to track that state vector. So that's one example of dynamics, okay? Perhaps there are other forms of dynamics that you can study, of course, but that's one example that we have studied that fits into your question. So it's possible. We have a diffusion version for Kalman type solutions that track the state of a model, the state vector of a model.
Okay, we're out of time. Those people who have a few more questions might head on down here. Otherwise, let's thank our speaker.
Thank you.